Okay, so this is a mini course. So I'll start out by reminding you of some things you know, maybe covering part of Alexi's lecture at half the speed, and then we'll move on to some new things. But sort of, I think it's a fun topic for this workshop because it's it's sort of obviously about harmonic maps, but at least for sort of the two-dimensional parts of the results, it's taking us into spectral geometry, and as we'll see in Misha's talk, into some new and I think fun applications to minimal surfaces in kind of classical settings. And also along the way, as sort of an analytic ingredient, we'll pass through some Ginzburg-Landau stuff, although not in the energy regime that the Ginzburg-Landau people like. Okay, but we'll sort of touch on a lot of fun topics that'll appear in several of the talks of this workshop. Okay. But we'll start to set some notation. So let's fix M and N, some, let's say, complete Riemannian manifolds. Okay, so throughout M will be sort of our domain manifold. It'll change, and the structure won't matter too much on that side until later. But N, we want to put a few more constraints on. So let's fix N to be closed, so compact without boundary. And let's fix an isometric embedding. Of N into some high-dimensional Euclidean space. So none of the geometric results we prove will depend on this embedding, but it'll be very convenient to have it around. And in fact, for some of our applications where N is the sphere, we really do care about having the sort of canonical embedding there. Okay, and so let me remind you of a definition you all know. So a smooth map, later we'll have to think about what happens when things aren't smooth, but let's start here. So a smooth map from M to N is harmonic. Well, if its critical point for the Dirichlet energy within the space of maps from M to N, right? Okay. So in other words, for all, if you like, compactly supported perturbations, U sub t staying in the map. So in particular, we can write this a few different ways. So U in C infinity of Mn is harmonic. Well, one way of saying this is that this pairing du dv, taking the derivative of the L2 norm of the gradient, this is going to vanish for all those v which arise right from variations which stay in the target. So this means v will have to take values in the tangent space of the target everywhere. So in other words, v is a section of the pullback bundle, right? So in other words, v of x belongs to t u of xn, okay? So this is equivalent to saying that the Laplacian of u is pointwise perpendicular to that tangent bundle, right? So Laplacian u of x belongs to u of xn perp at every point. And in fact, once you know that it's perpendicular, you can check that the only option is that Laplacian of u, okay, and here I'll have to explain my sign convention, but you can write it right as function of the second fundamental form of n at the point u of x, and then eating this sort of trace over derivatives of u, where ei is, say, some local orthonormal basis for the tangent space to n. Okay, so I should remark in my sign convention, this is a byproduct of spending too much time with spectral geometers, but Laplacian is always going to be d star d, right? So minus div grad. Okay. So for instance, in the case of the sphere, as Alexei mentioned earlier,
sorry, the
yeah.
equation is equal 0.
Yes, thank you. Yes. Okay. So for instance, if you're a sphere, right, then this tells you that if your target is a sphere, then this just tells you that Laplacian is pointwise equal to du squared u, right? So nonlinear with this quadratic term in the derivatives, but at least at first looks like a fairly mild nonlinearity. All right. So, and maybe I should remark that, of course, depending on your applications, you can also frame all of this in terms of things intrinsic to n. Right here, we're making reference to this this embedding in RL. Of course, you can also formulate it as with geodesics, just in terms of the geometry of n. For what we're doing, we're going to stick to this formulation, and of course, it's all equivalent. Okay, so let me continue telling you things you already know. So the most classical example, that's an important source of inspiration, is when our source manifold M is, say, an interval, or S1. And in this case, the existence theory for harmonic maps into whatever target we look at is pretty well understood. There are still open questions, but all of the analytic ingredients are pretty well laid down. So for instance, we have a classic result of Cartan from, I assume, the early 20th century. I don't know a date, right? That, for instance, every free homotopy class of loops maps from S1 into N contains a harmonic representative. Okay, so there are a few different ways to prove this, but the reason fundamentally why this works, well, there are a couple. The first, which is kind of key, is that if we're one-dimensional, if we're in a one-dimensional domain, then the space of W12 maps from S1 into N is going to be, well, we're in a one-dimensional manifold, so this embeds right into the space holder with exponent 1/2, S1 to N. So in particular, any finite energy curve is going to be continuous, and moreover, W12 embeds compactly, that's also crucial, into C0, right? Just via Arcella-Ascoli, if you like. So this means, first of all, if we just work in the class of finite energy loops, which is the natural space to work in for doing variational theory for the energy functional, we can make sense of homotopy classes. And if we have a minimizing sequence of curves in that homotopy class, well, we know, so let's take gamma j, a minimizing sequence. All right, so we know by Banach-Alaoglu that it converges subsequentially, weakly in W12, to some loop, which is going to be, well, we know also that by Arcella-Ascoli, right, if we pass to a further subsequence, we have C0 convergence. Okay, so we get a loop in the homotopy class. Of course, the energy is lower semi-continuous, so indeed, gamma infinity is in the homotopy class, and it's going to be energy minimizing in the homotopy class. Okay, and then it solves the geodesic ODE weakly, and it's not a hard thing to say that that's going to be a classical solution, right? Okay. So, of course, if you're trying to do more general variational methods beyond minimization, life gets a little more interesting, but not too much. So in particular, somehow because, so another way you could prove this theorem is using the gradient flow. And the gradient flow is also well behaved. So let me bring that down a little more. Right, so the geodesic gradient flow for the energy functional on S1, it's well behaved analytically. I'll formalize that by saying it's nice. So in particular, you can use sort of classical Morse theory, and I really mean classical Morse theory, right? This is in some sense the thing it was initially developed for, or Lusternik-Schnirelmann theory, you can just apply these sort of techniques out of the box and take information about topology of free loop space of your target manifold n, and apply these techniques and get existence results for closed geodesics. Okay, so for instance, this gives you, by the 1950s, the result of Lusternik and Fett. I'll put that as, I think, 53 or 54. That any closed NG admits a closed geodesic, right? A non-trivial one. Okay, so right, if your target has non-trivial pi 1, then you can just minimize as before. If your target has trivial pi 1, well, you still know some higher homotopy group will have to be there. And so if, let's see, is there a question? Okay. Question?
Is there a reason why cartography always say we did freedom multiple classes?
Yeah, right, so if you base things at a point, then things get, so the point, we really just want, a curve and anything that it can be continuously deformed to without any constraints. Okay. I mean, so in particular, if you do require it to, be based at a fixed loop, then you don't, if you just are critical point for energy within that class, you don't necessarily get a smooth geodesic through that loop, right? You could be like you could have a juncture there. Okay. So, right. So, yes, yes. So like closed, smooth maps from S1 to N, right? Smooth embedded image. Oh, no. These could be immersed. Yeah. Okay. Let's see. No, so this is at the level of harmonic maps. We're not doing embedded minimal submanifolds here. Okay. All right. So the point is, if pi 1 is non-trivial, then you can apply this. If you have some non-trivial pi k, then you get some higher parameter min-max you can do on free loop space and get a non-trivial critical point. So in other words, if you like, for the harmonic map existence problem, we have that for any target n, there exists a non-constant harmonic map from S1 to N. Right? So if you like, if you're thinking about blood types, then if you're type O, you're a universal donor. If you're type AB, with I guess the right plus or minus, you're a universal recipient. So this is telling us that S1 is a universal donor in the world of harmonic maps. Okay, so you can ask then about, what happens if we look at other targets and other domains, right? When we go beyond the world of geodesics. Okay, and there are lots of reasons to do this, and we'll think about some of them in a minute. But in particular, one of the results we'll be working toward in tomorrow's lecture, and we'll introduce some of the machinery today, is some joint work with Misha Karpukin from last summer, which is that universal recipients so ones which admit non-trivial harmonic maps from any domain include any sphere of dimension 3 or higher. Let's see, any Ricci positive 3 manifold, any higher dimensional manifold with positive isotropic curvature, and for instance, compact simple Lie groups. Right, so there will be an analytic condition which includes all of these as special cases. Okay, so in fact, there are lots of universal recipients out there too. All right, and we'll get more specific about that tomorrow. All right, so let's recall, though, the first main advance in variational methods for harmonic maps when you leave behind the classical sort of geodesic world. So the first sort of very general existence result for harmonic maps was, of course, the breakthrough by Eels and Sampson in the 60s, which also introduced the study of nonlinear geometric flows. So if you have a target with non-positive sectional curvature, then for any homotopy class of maps, let's put it this way, for any map U0 from M to N, there exists a harmonic map, still in the world of just smooth harmonic maps here, from M to N, homotopic to it. Okay, so if you're looking at targets more generally of non-positive sectional curvature, then every homotopy class has a harmonic representative. Okay, and the idea was run the gradient flow for the energy functional. Okay, so this is something you can write down in every case. And sort of the main thing that goes right in their work is that in a Bachner formula, if you're looking at the parabolic Bachner formula for the energy density, then the sectional curvature of N appears with a term that's quartic in du, right? So you have equation to the form Laplacian of du squared, in this case dt plus or minus Laplacian of du squared, something on the right-hand side, and the term that upsets you the most is the one which looks like du to the fourth, right? But that comes with a sectional curvature, and if that sectional curvature is non-positive, the sign is favorable. In your Bachner identity. So you get something that's going to be a subsolution of a nice problem. Okay, and so they get nice analytic control along the flow, and they're able to run it for a long time, and okay, you don't get quite smooth convergence in the limit, but then subsequently as you pass to infinite time, you get your harmonic map. Okay, and in fact, shortly thereafter, Hartmann showed that in the world of non-positive curvature targets, this is really the whole story, right? So we know, for instance, from the world of closed geodesics, that if you have a target of negative curvature, then each one of these minimizers is the unique geodesic in its class, right? So that generalizes. So Hartmann, a few years later, I'll say 65, maybe it's more like 66, showed that, I'll be rough about it and say a harmonic map U M to N in non-positive sectional curvature, maybe I'll say negative sectional curvature, is unique and then necessarily energy minimizing in its homotopy class, with, where the uniqueness could be sort of up to maybe some minor symmetry. Like in the S1 case, we can, of course, sort of rotate the S1, but that's it. Okay, so in particular, this gives you a very nice theory, which is useful for a lot of geometric applications. It also tells you that if you're trying to sort of produce lots of interesting harmonic maps via Morse theory, you're not going to run into much here, right? So we have sort of a clean dictionary. In this context, harmonic maps M to N just correspond to homotopy classes. Mn, right? Okay. So we can ask, well, when people were first studying harmonic maps, when they were first introduced in the 50s, the hope was to do something like Eels-Sampson in general. So given any map, can we always deform it homotopically to a harmonic one. In fact, before you start actually studying the analytic properties of this flow, you might even hope to do it by something like gradient flow methods in general, right? But the answer is no. So I think the first case this was observed rigorously in, this is, I think, Eels and Lemaire, is that there's no harmonic map from the 2 torus into the 2 sphere of degree, say, plus or minus 1. Okay? So let's think about what would happen if we tried to just minimize energy, to find a minimizer. Right, so let's go ahead and fix a metric here and say we're talking about the T2 with its flat square metric. Okay, so here's T2. Okay, and we want to find maps to S2 of degree 1. So first of all, by the area or co-area formula, we know that for any u of degree 1, right, remember this is half du squared, well, this is going to be bounded below by determinant of u star du, or if you like, the pullback, right, of the volume form. Right, and this is degree 1, so that's just going to be 4 pi. Right, so we have a universal lower bound by 4 pi. And in fact, it's not hard to convince yourself that we can get as close as we want to that bound. Right, how can we do that? Well, here's a crude way. Let's take our square torus. Let's cut out a little tiny disk here around the origin, say, and then we can map that conformally by some stereographic projection and scaling to our usual S2 with, say, a little neighborhood of the North Pole cut out here, right? So this over here is conformally covering all of this, and then we can just sort of squash everything out here to this little region here, right? Okay, and this part's conformal, so the energy here is going to be around 4 pi, right? It's 4 pi minus that little bit of cap we've removed. And then out here, the energy is going to 0, right? So we have all of the energy concentrating around this point. And if we rescale, we end up seeing the identity map from S2 to itself. Right? So there's the OR example of bubbling phenomena. So if we take a minimizing sequence, we end up with this bubbling picture or some version of it. Okay. So one of the problems here, when we're trying to actually carry out these constructions analytically, and for most of today's lecture, we'll stay in this 2-dimensional setting and then move into supercritical dimension tomorrow. But if we're working on 2-dimensional domains, then we know, as Alexei was reminding us this morning, that the energy is conformally invariant. From 2-dimensional domains into whatever target you're looking at, right? So that means 2 things. The first thing is that if we precompose the conformal automorphism here, then the energy is preserved. And it also means if we change the conformal class of our metric here, right, energy is preserved as well. Okay, so it has a lot of symmetry. And symmetries can be a good and bad thing, but we know they tend to kill compactness results, right? Okay, so in particular, W12 is borderline for embedding into C0 here in dimension 2. Okay, since we're borderline, we can try perturbations that take us just above the border. And so the first people to implement this were Sachs and Uhlenbeck. Okay, so let me remind you of that story. Okay, so an idea, let's say you're trying to do this minimization argument, but in a serious way. The idea of Sachs and Uhlenbeck is, well, we would like to have a better behaved space than this W12, which isn't quite a Hilbert manifold and doesn't really embed into C0. Of course, since we're borderline, if we jump up just a little bit to W1, 2 plus epsilon, then we will embed compactly into C0, and so we have some hope for, we can minimize there and then see what happens when we take a limit. Right, so that's the idea. So more precisely, they looked into minimizing the alpha energy. When I was trying to remember the conventions, when I was preparing this, I Googled alpha energy. Apparently, it's the name of some kind of cologne that's supposed to make you smell like an alpha male. I don't think that's what they had in mind when they came up with this. But right, the idea is to take the usual energy and just bump it up by a little bit to make things supercritical, right? So du squared, we'll add a little constant out here just to regularize things a little bit more. Okay, and then this, okay, so this is the convention where alpha is bigger than 1, right? Okay, right, so note that if we take alpha equals to 1, then this is just the regular Dirichlet energy plus a constant that we won't see. But in general, we can minimize for fixed alpha, and we get a smooth map. It's going to be in the right homotopy class, use of alpha, and it's going to satisfy, you have some nice perturbation of the harmonic map problem, right? So let's see, probably an alpha minus 1 over 2 there or something. Right? Okay. And then the idea would be, well, now you have a distinguished minimizing sequence, right, that solves some PDE, so you can look at what happens as alpha goes down to 1, right? And the answer is, well, either you get smooth convergence or you have exactly this picture, right? So in particular, they had, to make that precise, they have so-called epsilon regularity theorem. Okay, so there's some universal epsilon naught depending on n, right, such that if U alpha solves, let's give this a name, star sub alpha, let's just say on a disk of radius r, right, or maybe really this could be some geodesic disk in our domain, but let's just stick with the flat disk in R2. It's the same picture because it's all at small scales. Then if our energy is less than epsilon naught there, then we have we have not just smoothness, but we have estimates. So C1 estimates, and in fact even better ones that we can pass to limits. Right? So if our energy is not concentrating on these disks at small scales, then we have nice estimates and we can pass to smooth limits. And if it is concentrating, then we can choose a scale at which to rescale. And as in this picture, if we rescale appropriately, we end up just seeing maps from R2, right? So rescaling gives non-constant finite energy harmonic maps from R2 into N, right? But R2, well, up to removing a point, it's conformally the same as S2, right? So up to stereographic projection, and the removability of point singularities, this gives you an honest, smooth harmonic map from S2 to N. Okay. So if you're trying to produce harmonic maps from S2 in the first place, so in other words, branched minimal immersions from the two-sphere, well, you're kind of in good shape because reach for the stars, and if you fall, you land on a cloud, right? So if you have energy concentration, you're still getting a non-trivial harmonic map at the end of the day. And so for instance, if you're running some min-max construction, then you get some sequence of solutions to this alpha problem. They'll come with energy bounds and Morse index bounds. And it's not hard to see that either you end up with something here, right, that retains those energy bounds and Morse index upper bounds. Or if you do have energy concentration, then you get a different harmonic map from S2 to N, but it'll still have the same upper bounds on energy and upper bounds on the Morse index. That's a much easier statement than the ones that Alexei was talking about this morning, right? Showing lower semi-continuity of Morse index that it can only drop in the limit is just an easy argument using log cutoff functions. Right, so in particular you get results like the famous Sachs-Uhlenbeck existence result. Right, which tells you that if pi 2 of n is non-zero, then n has a non-trivial stable harmonic map. In other words, a branched minimal two-sphere. And more generally, by running min-max versions of the same argument, if pi k of n is non-zero for k bigger than or equal to 3, then n has a non-constant harmonic map S2 into n of index at most k minus 2, right? So this part was famously exploited by McAuliffe and Moore in their proof of the sphere theorem for positive isotropic curvature. Okay, so summarizing, every non-aspherical, right, so everything that has some higher homotopy group beyond pi 1, every non-aspherical closed target n admits a harmonic, or if you like, a minimal two-sphere. Okay, good news from the perspective of existence theory for minimal two-spheres. On the other hand, this is going to be a bad news if you're trying to produce harmonic maps from things other than the two-sphere and see these coming up via energy concentration. Okay? So this is good news for minimal two-spheres, potentially bad news for harmonic maps from other targets. Okay. So that's sort of the story for the Sachs-Uhlenbeck perturbation. Not the whole story, of course. People have said lots of other things. But now I want to go to a different regularization that, first of all, works on domains of arbitrary dimension, which is one big advantage over the Sachs-Uhlenbeck perturbation. But even in dimension 2, which is kind of where we'll stay today, it's useful in that it regularizes, but regularizes in a different way. Okay, so this is a so-called Ginzburg-Landau type perturbation. Okay, this is always obnoxious. There are about 12 different things in geometric analysis that get called Ginzburg-Landau. Of course, if you go back to the 1950s, they all spring from the same source. You can permute them and make it Landau-Ginzburg, and that's a whole other thing. What I'm talking about today is really just the version that's relevant to harmonic maps. Okay, so let me just sort of advertise what the features are here. So if we're comparing the alpha energy Cologne approach and the Ginzburg-Landau perturbation of variational theory for harmonic maps. Okay. Well, first of all, as I mentioned, sort of one obvious limitation here is that it's specific to surfaces. When your domain has dimension 2. Okay, whereas the Ginzburg-Landau, as I mentioned, this is going to work in arbitrary dimension. That's one piece of good news. But there's also, even in dimension 2, a difference that's just sort of a qualitative difference between these two perturbations, and different ones are useful depending on what you're trying to do. So the alpha energy, it regularizes, it gets rid of your sort of bad singular formation bubbling behavior here by penalization. So if you're doing some variational methods for your alpha energy, and it sees you trying to bubble here, well, it punishes you by hitting you with infinite energy, and it prevents you from doing that. The Ginzburg-Landau regularizes by relaxation. So what it's going to do when it sees you engaging in this bubbling behavior is it says, well, that's okay, but I'm going to mollify you and just make you a map into the ball here instead, so you'll be a smooth map into the ball instead of a singular map to the sphere at the end. Okay? And this is in particular where our embedding into Euclidean space for our target starts to really come in handy. Okay, so now recall that we have this isometric embedding floating around of our target n inside of RL. Okay, so in particular we can define a distance squared function, giving us the squared distance to n, d sub n squared from RL into n, so something that's vanishing along n and giving us the distance squared everywhere else. And then we know that this is going to be sort of smooth, it's nice and well behaved, where the nearest point projection is well behaved, so on some tubular neighborhood, so some delta neighborhood inside of RL for some small delta. Okay? So let's go ahead and define a function that's going to hurt you if you're going too far from n, and will hug you if you go close. So this is, let's call f of y, this function from RL to R, which looks like, let's say, dn squared of y over 2 if you're inside this nice tubular neighborhood. Let's go a little bit further inside and say b delta over 2 of n. If you're far away, very far away, say this is going to be some large constant on, let's say, RL minus the ball of radius delta, and then some reasonable interpolation in between on sort of this annular neighborhood b delta of n minus b delta over 2, which is, let's just say, sort of non-increasing in the distance. Okay? Yeah.
So dn squared takes values into R or into...
Oh yeah, thank you. That's right. Yeah, I'm surprised I've only been caught on these things like 2 or 3 times so far. I'm sure it's been like 20. Okay. All right, so now let's define our so-called Ginzburg-Landau functionals, which are really introduced in this form by Chen and Struve, who were interested in regularizing the harmonic map heat flow to deduce the existence of weak harmonic map flows in some generality. All right, so for epsilon bigger than 0, we define a functional E sub epsilon from W12 maps from M into RL. Right now, this is just our nice Hilbert space, literally a linear Hilbert space of RL valued maps in W12. And what does it do to them? Well, if they're taking values in the target, then it's just the energy. We just get half of du squared. But if they're not taking values in the target, we want to punish them a little bit for that. And so we make this f of u over epsilon squared here. Right? So if they're really sort of taking values far from the target everywhere, right, then this is going to be like 1 over epsilon squared. And as epsilon goes to 0, that's going to blow up. Right? And we're always going to be now in the bounded energy regime. OK, so this is, I guess, in principle a course. So let me give you an exercise. So exercise E epsilon is a C2 functional on this Hilbert space, right? It satisfies, I'll be vague and say A Palais-Smale condition. OK, so if you want to be precise about it, I guess I am assigning an exercise, right? So I'm not going to grade these. If we have a sequence with E epsilon prime of uj going to 0 as functionals on W12 dual, right, in the dual of this Hilbert space, then let's say with an energy bound, and this is not actually somehow a serious thing, but just to make sure you can do the exercise with an L infinity bound too. Then subsequentially, uj converges strongly to critical point, right? OK, just reminding you what Palais-Smale looks like. So in particular, if we're trying to do min-max theory for these functionals, well, their gradient flow is well behaved. They have nice compactness properties that tell us that sequences of points which are almost critical converge to critical points. So we know off the bat that we can do variational theory, classical sort of Morse-Hallucination-Neuralman theory for these functionals. OK, so critical maps, u sub epsilon, satisfy an equation, right? They look like Laplacian of u plus gradient f of u over epsilon squared is 0, right? This is a very mild nonlinearity, and in particular, it's easy to see that these are going to be, they solve these weakly a priori, right? But weak solutions are smooth. They'll always be taking values inside this sort of tubular neighborhood we started with, well, depending on how we set it up, but OK. They'll always be taking values inside a fixed compact set anyway, containing our target. OK, so what's the goal? The goal now, so variationally, it's not hard to convince yourself that as I'm taking epsilon goes to 0, I'm forcing these maps to take values in my target. And then at that point, once they take values in the target, I'm just doing variational theory for the energy, right? So it shouldn't be hard to convince yourself that these should be converging in some sense to harmonic maps to n. On the other hand, if you're looking at the equations, that's maybe not quite as convincing right off the bat as in the Sachs-Uhlenbeck case, because now we're taking Laplacian is equal to the sort of thing that looks like it's blowing up like 1 over epsilon squared, right? So let me maybe let's see. Question? All right, OK. So let me make a little claim. To give you some flavor of why you can expect this convergence. So if u epsilon solves this equation, let's give it a name, star sub epsilon, with let's go ahead and be really kind to ourselves and impose, let's say, W2P bounds for P large, okay, and bounded energy. Then U epsilon will converge subsequently to harmonic map from M to N. Okay, so what's the punchline here? The point is that at that level, you have, you'll have, say, at least C1 alpha convergence, so in particular C0 convergence. So you know that your maps will be taking values always in this tubular neighborhood, where this F just looks like distance squared, right? So you'll have some equation of the form delta U epsilon plus, well, distance nabla of the distance over epsilon squared is equal to 0. And the point is that, right, this here, this is going to be perpendicular to the tangent space at the nearest point projection of U epsilon to N, right? Okay. But then we have enough regularity from sort of what I've imposed up here, and if we don't have enough, add a 3 there or something if you like. I think this is actually enough though. We have enough regularity here that when we pass to limits, that's going to be preserved, right? So the boundedness of this energy means that, well, distance squared of U epsilon over epsilon squared is going to be bounded, means that in an integral sense at least, U epsilon is converging to a map which has to take values in N, otherwise this would be going to infinity. So we know U has to take values in N. And then this condition here, if we've imposed enough regularity here, passes to the limit, right? This being perpendicular to that tangent space. So this tells you that Laplacian U of x is perpendicular to the tangent space of U of x of N. Okay, which tells you that you're harmonic. Okay, just so it doesn't seem super mysterious, that at least in the range when we have smooth convergence, right, we get a harmonic limit. Okay. Of course, just as with this Ax-Uhlenbeck perturbation or any reasonable perturbation, we can't perturb away the intrinsic problems with the harmonic map equation. So we don't expect smooth convergence when we carry out general variational constructions. And instead we have epsilon regularity type results. Okay, so let me not say too much about those, but maybe I'll just say sort of key ingredients. What are the key facts? The fact is we have a monotonicity for the n-2 density on small balls. So in particular for a Euclidean space, then we have something like this. Right, so if this is our energy integrand, then this is bigger than or equal to 0, right, on small balls. And of course, if we're on a manifold, we get some little error that we don't mind too much for blow-up analysis purposes. Right, so we have this monotonicity, and moreover, we have a nice Bachner identity. Right, which in particular, with a little work, gives us an estimate of the form Laplacian of our energy density is bounded above by some universal constant times that energy density plus its square. Right, if we had just that linear control, then everything would be sort of uniformly smooth and life would be done. But the catch is that as with harmonic maps, as we should expect, right, we have this quadratic term in the right-hand side that prevents us from just getting straightforward gradient estimates. But, we have the following PDE exercise, which gives you epsilon regularity theorems in many different contexts, right? If you have f from m to, let's go ahead and make it non-negative, right, satisfying, let's say d star df is bounded above like some constant a, f plus f squared. Okay, and the supremum of this f integrand over all balls contained in some bigger ball is less than eta naught, depending on a sufficiently small, maybe a and m here, right, if we're fixing our domain manifold m, then we get an L infinity estimate on balls of, say, half that scale. Right, so the statement is that there exists some eta naught, or if you like, some epsilon naught, such that as long as you clear these two thresholds, then you have L infinity bounds at the appropriate scale. And then once you have, right, so in particular, the Bachner identity gives you this part, monotonicity gives you this part for your energy density, and then once you have L infinity bounds, as in the case of harmonic maps, it's not too hard to promote that to higher regularity, and really the point here is higher regularity with uniform constants, right? Because of course we know we have smoothness a priori. The question is how well it's preserved in limits. Okay, so if we're in higher dimensions, this is the starting point for, wait, let's see, I won't take this off because then I'll mess with the microphone. Okay, then this is the starting point for a sort of more complicated story where bubbling gets a little more dire. But for the rest of today's lecture, I want to give you some applications of this machinery in a two-dimensional setting, which turn out to have lots of interesting applications in spectral geometry, and as we'll see in Misha's talk tomorrow, turn out to have some very useful applications for constructing lots of new minimal surfaces in some very classical settings like the three-sphere and, for instance, the free boundary guys in the three-dimensional ball. Yeah.
What is the lowercase e represent?
Oh yeah, I should write that somewhere. So this, I just mean the integrand and the energy here, right? So this is E epsilon of u is going to be like du squared plus the penalization, right? And in fact, once you start doing the analysis, you see that we could really get away with sort of, for the most part, doing everything with du squared. But, okay. All right. Okay, there's sort of a natural breaking point. Any questions so far besides that? All right. Everyone's on board. That's good. I started slow enough. Okay. So now let's specialize our targets a little bit. We're going to be looking at harmonic maps m to Sn. We're going to be thinking about applications in spectral geometry. It occurs to me that in France, harmonic maps and applications probably looks redundant, but that's all right. Okay, so let's sort of jump to the spectral side. So given a closed two-dimensional surface, let's define lambda k bar of M2G to be the kth eigenvalue of the Laplacian, our favorite sequence of geometric invariants, times, well, that has some scaling, so let's introduce something to make it scale invariant. Let's normalize by the area. Okay? So in recent years, well, going back to the 70s, but sort of picked up dramatically recently, it's been observed that these have a remarkable variational theory on the space of metrics, which has some intimate applications to minimal surfaces and harmonic maps. Right, so the first big result was Hirsch in 70 who observed, by sort of a comparison argument, that lambda 1 bar for any metric on the 2-sphere is bounded above by 8 pi with equality if and only if that metric is round, right? Constant curvature. Okay. In the decade that followed, Berger got interested in this problem of trying to maximize these quantities over other manifolds. Yang and Yao famously observed, well, they observed much more than what I'm going to write down, but in particular, lambda 1 bar of mg has a bound just in terms of the genus of our manifold, right, without reference to metric conformal structure. So there always is a supremum. Of course, they can say more. They can say some specific linearity in the genus. And then following shortly thereafter, Li and Yao introduced a very useful invariant known as the conformal volume, which sort of generalizes the tricks that Hirsch and Yang and Yao were using to get these estimates. Okay, so let's maybe introduce it first. Okay, so given some conformal structure on our closed surface, and given some n at least 2, let's define the nth conformal volume as follows. Okay, to be the infimum over all branched conformal immersions of our surface to the n-sphere. Right, so conformal immersions, or maybe we allow it a few branch points. And then the supremum over the group of conformal automorphisms of the n-sphere of the areas of the images of this M under this map, and we move it around by those conformal automorphisms. So the area of G of phi of M. Okay? So equivalently, let's observe. We can write this a little more compactly. So to the conformal automorphisms, they're generated by isometries, which don't change the area, and by conformal dilations. Right, so for every point y in the open n plus 1 ball, we get a conformal dilation, a conformal map of the n-sphere, which takes a point x in the n-sphere and sends it to 1 minus normal y squared, x plus y over x plus y squared plus y, okay? So if the formula looks weird to you, you can stereographically project to send y to the origin, and then these are just dilations in Rn, okay? All right, but all right, since these generate the conformal automorphism group modulo isometries, we can write Vc of mgn equivalently as, okay, still the infimum over all these branched conformal immersions. And then now just the soup over these n plus 1 parameter families. Okay, and then we can observe, right, everything here is conformal. These maps are conformal, this map's conformal. So that area is going to be the same as the energy of G composed with phi, okay? So it's a min-max quantity for the energy functional, but over the sort of very restrictive family of conformal maps. So their observation, generalizing the Hirsch and Yang-Yao tricks, is the following. So, well, they had sort of two families of results. One is using this to get lower bounds in the Willmore energy. And the other is upper bounds for these conformal maxima. So given m2g, n bigger than or equal to 2, we have that half, let's call lambda 1 of m brackets g the conformal max of this first eigenvalue. That's always going to be bounded above by this conformal volume. Okay, and if you have a minimal immersion of conformal minimal immersion into Sn by first eigenfunctions, then you have equality with both of these just being given by the area. Okay? All right. So, and the idea here, at least for the lower bound, is a very simple topology one. And it's the same one that Hirsch had back in 70, but just sort of generalizing the machinery a bit. Let's see. Okay. So, right, the idea is that for each metric G and G, and any conformal immersion phi from M2G to Sn, we have, well, we can look at this family. We see that the map sending y and bn plus 1 to g sub y composed with phi well, if we look at the boundary behavior, formally, if x is a point far from y, then as y goes to the boundary, this 1 minus norm y squared is going to go to 0, and we're just left with the constant map to y. Okay? So as a family in L2, with respect to whatever metric we've chosen here, so in particular, we can extend to a continuous family from the closed unit ball, let's say f sub y, where for y in the boundary, we're just that constant map, right? So where f sub y is equivalent to y for y in the boundary n plus n sphere here, right? Okay, but now let's just consider the map sending bn plus 1 into bn plus 1, which takes y and sends it to the average of fy. Right, so this is going to be a map from bn plus 1 into bn plus 1. And by our boundary conditions, right, just being the constant map on the boundary, this is going to be identity on the boundary, Sn to Sn. Okay, so elementary topology, right, the identity map from Sn to itself is not null homotopic, so this has to have a 0. So in particular, right, this tells us that there exists some y in bn plus 1 such that this average is 0 as, you know, a vector in Rn plus 1. So in particular, each of the component functions are going to be test functions for the Rayleigh quotient. Right, so we're going to know then that by the variational definition of the Rayleigh quotient, integral of df squared is bounded below by lambda 1 Laplacian of g, integral of m f squared, but f is sphere valued, right? So this is just lambda 1 bar of mg, and then this map is all conformal, right? So we get twice the area of fy here, which is going to be bounded from above by the sup over all of the y's in the family of that energy, right? So taking the infimum over all these families, we see that the conformal volume is bounded below by this guy, right? Okay. And so for some conformal types, this gives us nice sharp bounds on this lambda 1. So in particular, they use this to show that the conformal max on RP2, where there's only one conformal structure, is also realized by the round metric on RP2. Okay, and it allows you to classify the conformal max of lambda 1 whenever you're in a conformal class which has one of these branch minimal immersions by first eigenfunctions to the sphere. On the other hand, if you're really interested in studying general conformal classes, or in particular taking the sup over all conformal classes, then this is not sufficient. And here, the first sort of real breakthrough that goes beyond these techniques was by Nadarashvili in the mid-90s. So he proved a conjecture of Berger's that on the 2 torus, where now our space of conformal classes is 2-dimensional, lambda 1 of T2 is realized by the flat equilateral torus. So let me draw an equilateral triangle. And then let me draw this guy. Okay, so by this one. And the way he proved it was by essentially the way we try to get our calculus students to solve maximization and minimization problems. He first argued that a maximizer exists, discussed what maximizers have to look like, so some kind of degenerate Euler-Lagrange equations, and then he was able to appeal to a classification of those solutions by Montiel and Ross. And really the essential observation was that if G maximizes this lambda 1 bar of mg conformally, so it restricted to a conformal class, then, well, the first thing you could say is that there's a collection of first eigenfunctions whose sum squares to a constant. Another way of putting that is that there exists a harmonic map from phi from mg to some sphere, right, whose dimension has a universal bound that grows with the genus here by first eigenfunctions. Okay? So in particular, right, if you have a map solving this, well then its Laplacian is clearly pointwise perpendicular to the tangent space, so it has to be harmonic, right? And if we can do a little better, if instead of just maximizing in the conformal class, we maximize globally, so if it maximizes this lambda 1 bar over all metrics, then you have such a map which is also conformal. I guess with respect to this metric, it would be actually an isometry or a homothety. Okay. Okay, so So in particular, this gives you a minimal immersion from M to Sn by first eigenfunctions of the Laplacian. Okay? So it's kind of a bizarre critical point condition. But in particular, Montiel and Ross had already shown in the 80s that in the case of the torus, the only two options were the flat square Clifford torus inside of S3 and this equilateral one minimally embedded in the 5 sphere. And so you can just compare directly and see that that one wins. Okay. So in higher genus, not a lot is known. We know the maximizer for the Klein bottle and for the oriented surface of genus 2. But beyond that, that's essentially all we can say explicitly. But we do have the beginnings of a good existence theory. And so a lot of this was laid out by one of the organizers, Romain Petridis, in 2014. All right, so we showed in particular that within a conformal class, there exists a lambda 1 bar maximizing metric. Here metric has to get a little asterisk in general, but the asterisk is not one that's going to bother us too much. Okay, that asterisk really means there could be some finite collection of conical singularities, but those are somehow very mild and don't disturb our estimates or anything. And moreover, if on, say, the oriented surfaces M sub gamma of genus gamma, we have that the global max lambda 1 of M sub gamma is strictly bigger than the global max on gamma minus 1, then you have existence here. So this somehow prevents your maximizing sequence of conformal classes from degenerating to the boundary of Teichmuller space. Right, so you have a globally maximizing metric that's going to give you some branch minimal immersion. Okay? So there have been valiant attempts to prove this, basically by trying to start from a maximizing metric on the lower genus surface and attach handles in a very clever way to sort of get something which directly has lambda 1 bar exceeding lambda 1 bar on the low dimensional thing. But for now, this is still open. And I'll discuss some new methods, and it'll also show up in Misha's talk for proving this, or proving variants of this in some situations of interest that go through the variational theory of harmonic maps. Okay. So let's start with an innocent question, which is all right. We have this bizarre thing that we have this intrinsic variational problem on the space of metrics on our manifold. And if we do this conformal maximization, we end up with a harmonic map to a sphere. So we end up with this critical point of the energy functional, but we haven't done anything with the energy functional to get it. So an important moral over the last decade, coming from, for instance, Marquez and Neves' proof of the Wilmore conjecture, is if we have interesting critical points of some geometric functional, then often we can extract more information by understanding their variational characterization. All right, so that's a sort of an initial goal here is how do these harmonic maps arise variationally? Okay? And the answer is going to boil down in some sense to revisiting Li and Yao's conformal volume. So they give us this min-max quantity, which we can view as a min-max quantity for the energy, giving us a nice universal upper bound on this conformal max. And the idea is that if we relax their min-max, right, so here they're taking this very restrictive family of test maps to plug in. If we sort of relax to look at everything conformal to the, homotopic to those, then maybe we can upgrade that inequality to equality. Okay? So that's the idea. So let's consider this, let's say, script f sub n to be the collection of families parameterized by the closed n+1 ball. We get a family of maps. And what we're going to want to do is mollify the Liao construction and do a Ginzburg-Landau type relaxation. So these are going to be honest continuous families in W12 from M to Rn+1 with, again, this boundary property that U sub y is just the constant map to y for y in the boundary. Okay? So if we mollify the Liao families, we get examples of these. Okay, but of course, we get many, many more as soon as we drop all these conformality requirements. Okay. And then for the spherical Ginzburg-Landau energy, so here are, instead of using the distance function, the sort of canonical choice is we do energy plus 1 minus u squared squared over 4 epsilon squared. The precise choice doesn't matter too much. If you wanted, you could build this out of distance functions instead. Okay, then we define these min-max energies E sub n epsilon of mg. Notice that off the bat, they depend on the specific metric we're choosing to be the infimum over all such families of the max of E epsilon. Okay, so because you've already by now done your exercise to check that these E epsilons are nice, smooth, Palais-Smale satisfying functionals, we can say that this E sub n epsilon for n bigger than or equal to 2, as soon as these families are non-empty, is realized by a critical point, U epsilon Rn+1, whose, well, its energy is going to agree, right? That's sort of what it means to be realized. And critically, it's also going to have a Morse index bound, an upper bound, along the lines you expect, right? These are n+1 parameter families. So it's going to have, as a critical point, the index of the Hessian there is going to be at most n+1, right? So it's growing like the dimension of the sphere we're mapping into. Okay. And then what's the idea? Well, let's define E sub n of mg to be, if you like, the limit as epsilon goes to 0 of these En epsilons. Okay. In fact, you could also write this as the sup over epsilon. You can see this is an increasing sequence in epsilon. And then, well, what do we see? We can observe that, all right, this term, this is conformally invariant. This term here, this potential times the area, well, that depends on the metric, the specific choice of metric in the conformal class. But if we change the metric, we always know that for any two conformal metrics, we'll have that g tilde is, going to be less than or equal to some constant times g, is going to be bounded below by some other constant times g, right? And we'll see that we can always compare E epsilon with respect to this metric to like an E epsilon over C for this metric, right? So we take the limits of epsilon goes to 0 or epsilon over C as epsilon goes to 0. It's the same thing. So the punchline is that as epsilon goes to 0, we get to ignore this part and these become conformally invariant. So we see that this is actually a conformal invariant. So that's already good news. Moreover, okay, so to observe in particular that it's finite, we can observe that by mollifying the Li-Yao families, we have this going to be bounded above by the conformal volume. And the same trick that Li-Yao used, the same elementary topological argument, will still go through with some epsilon terms that will go away as epsilon goes to 0. Yeah?
If you just come back to the flat case in R2,
Yep.
and you know in the limits, like I get it because in the renormalized.
You're thinking about the like R2 valued Ginsburg-Landau, and that's right. So yes, so for instance,
The concept would depend on your second guy because you know there's some gamma that.
sure. So for instance, if I were trying to do this for maps to S1, then this family would be from my dissertation, essentially. We're doing the R2 valued version. And then you get log epsilon blow up, which is natural, and some concentration around minimal varieties.
The renormalized energy would depend on the metric.
Absolutely, absolutely. No, so the point is, though, as epsilon goes to 0 in the bounded energy regime, which is the natural regime here, then this just, reduces to the conformally invariant problem and everything behaves like harmonic maps. That's right. So if you're trying to do this, if you're doing this to try where your target is, 2 points, then it's the Allen-Kahn thing and things are blowing up along minimal hypersurfaces, and that's right. But the point is we're in this bounded energy regime where everything behaves like harmonic maps. Okay. So an immediate punchline is that, as with the Li-Yao argument, this is going to be an upper bound for eigenvalue problems. So in particular, claim is that for any bounded linear functional on W12 in our manifold, we have that you can use the same trick that Li and Yao use, essentially, to see that there exists some u W12 from M to Sn such that all of the component functions are in the kernel of T. And their energy is bounded above by this min-max energy. So in particular, you have that this conformal maximum is bounded above by this min-max energy. But you also have, in fact, much more, right? Because taking this, so you get this by taking T to be integration against a positive weight function. But of course, there are lots of functions in W12 dual other than, nice, smooth positive functions. So it gives you sort of a strengthening of that statement. Of course, you could also use these in the Li-Yao case too. This is just an observation. All right, but the point is, all right, so you have this bound more or less for free. The kind of key insight is that once n gets large enough, unlike the conformal volume, this actually gives you equality in an arbitrary conformal class. So for n sufficiently large, this min-max energy, is defined sort of naively in terms of variational methods for the energy, coincides with the maximum of this normalized first eigenvalue in the conformal class. I should have a factor of 2 here just because of my conventions. Okay. So let's see. I could start telling you about a bit of the proof. Is it going to 125 or 130? How do you want to do it?
You have 5 minutes.
Okay, so I'll start telling you some ideas. Okay, so let me sort of give you, so for those of you who have taken a look at this first paper where we prove this statement, there's some good news, which is that the most technical part can be streamlined a lot. So in particular, that sort of comes down to the following. So we have these critical points of the E epsilon energy functional with Morse index n plus 1. So in the original paper, what we were doing is, well, first we did some bubbling analysis as epsilon goes to 0 with n fixed, and we have to use the index and information about the energy to try to rule out most of the bubbles, although a priori we still had some possible bubbles in low dimension. And then we had to do a more complicated bubbling analysis as n goes to infinity to give us some kind of uniform control on the gradients to lead to some kind of stabilization for these maps as n goes to infinity. So it turns out we can streamline that dramatically, and using the index bounds just at the epsilon level intelligently, we can get the rule out bubbling as sort of epsilon goes to 0 and n gets large altogether, just using the index bound at the epsilon level. So maybe I'll sketch out a little bit of that. So claim, so for some universal constant c, writing g sub n epsilon to be the conformal metric, it looks like 1 minus un epsilon squared over epsilon squared times the metric that we started with. We have that the first eigenvalue of the Laplacian for this conformal metric is going to be bounded below by 1 minus c over n. Okay? So the fact that we have a positive lower bound is already sort of give us some condition that we can only have at most one bubble. And then once we take n large enough and use a little more information coming from Romain's work, that'll also allow us to sort of immediately rule out bubbling as n goes to infinity without any deep work. So I'll just quickly sketch some of the computations that go into this proof, and then leave us there for now. So the idea is, okay, so there's a classic result of El-Soufi giving us index bounds of sphere-valued maps where the sort of deformations that you use are just the conformal automorphisms of the target sphere. So the idea is to use sort of weighted conformal automorphisms, except now these aren't really sphere-valued, so they won't quite be that. But the idea is to, given a smooth function on M, and some vector, any vector, in Rn plus 1, consider the vector field v phi comma w, which is phi w, the constant guy, right, minus u dot w times u. Right, so if phi were just 1 and u was actually sphere valued, this would really be sort of the tangent field to some conformal automorphism, some conformal dilation. Okay, so the idea is, okay, this is I guess another exercise for you. We can write E epsilon double prime of u applied to these fields. And these give us, this is just a computation you can do, d phi squared minus 1 minus u squared over epsilon squared phi squared. So notice this is exactly sort of the terms that'll come up if we're looking at eigenvalues for this delta g and epsilon, then we're exactly estimating Rayleigh quotients where this is the numerator and this is the denominator, right? And then plus some term, I'll just say j sub u of w comma phi, where the punchline, since we're running low on time, is that you can show by sort of taking a trace that for most w, that's right, so for a fixed phi and for most w, by sort of taking a trace, this is bounded in terms of this one. And so for most w, this is going to be like 1 over n times this term. So you get this is going to be like 1 plus c over n times this term for most w. Okay? And then the idea is we take sort of the span of all possible variations of this form, where phi naught is 1, say, and phi 1 is the first eigenfunction for this delta gn epsilon. And the point is that you can show that there's a common collection of w's that's together gives you a family here that's larger than n plus 1, such that if this didn't hold, then you would violate this, this inequality. And so you use the index less than equal to n plus 1 to get this information directly on the first eigenvalue of this new metric. So now you have control not only from below by first eigenvalues of metrics, but you're also going to get control from above, as I'll maybe make explicit next time. And so immediately you get, as n goes to infinity, you get the equality here. And you also get some new analytic tools to help you prove that stabilization for n large. But I'll pick up there next time.